This next section on polar coordinates is really just a review of what you probably already learned in trigonometry, but given that it could be a few semesters behind, it's worth reviewing before we go into the calculus of polar coordinates so that everybody's on the same page. So what happens is that the rectangular coordinate system is really only one of many different kinds of possible coordinate systems to locate points on a plane. One other that's very common and useful is the polar coordinate system. And the polar coordinate system locates coordinates by measuring the distance from the origin, we label that r, and the direction angle rotated from the positive x-axis, and we name that theta. So to give you an idea, our polar coordinates will always have the form r and theta. And let me make that a little larger. And it looks similar to a rectangular coordinate point, but it's interpreted differently. Our rectangular coordinates look like just x and y. But there's a clear way of transforming between the two systems. So for instance, on a rectangular grid, if I have the point P, which has the coordinates x and y, I can figure out what the value of r and theta are using a little bit of trigonometry. So for instance, r, based on a set of rectangular coordinates, is the length of a hypotenuse of a triangle formed with lengths x and y. So the length of this hypotenuse would be the square root of x squared plus y squared. So that's a pretty common transformation for going in rectangular to polar. Then for the direction angle, we use the arctangent of y over x. And arctangent isn't special here. You could use any of the other trig functions as well, but we already know the values of y and x, so it makes a lot of sense to use tangent. And that way you don't have to calculate r first and then go from there. Now, going the other direction with polar coordinates into rectangular, we use a little right triangle trigonometry as well, and we can determine the x-coordinate from a polar coordinate set by doing r cosine theta. And you can show that pretty easily just by using a little bit of right triangle trigonometry. So for instance, here's a right triangle with side lengths x, y, and r, and the angle measure theta, if I try and determine the cosine of theta, which is to the adjacent side over the hypotenuse, then I can very easily see that r cosine theta is the value x. Similarly, y is r times the sine of theta. And so that's how we transform to and from rectangular and polar coordinates, which I'll do a few examples of in just a moment. I would like to talk a little bit about graphing first. In trigonometry, we generally have very specific bounds on our values of polar coordinates. So for instance, r is generally considered to be only a positive number, but really negative numbers are allowed. You just move away from the origin in the opposite direction when you determine your direction angle. Theta is generally considered to be a value in the range 0 to 2 pi, but again, that's not really a requirement. It can be outside of that range. It just gives you an equivalent angle that would be coterminal with the provided angle. So to plot a couple of points here, we have a polar coordinate grid. And what I want you to see is that if you take away the two restrictions above, so if you allow for r to be negative, and if you allow for theta to be outside of the range of 0 to 2 pi, then you don't have unique values for individual points. So for instance, the point 2 pi over 4. So if we look at the line pi over 4, that's right there. Positive 2 pi over 4, that's easy to find. We just go out 1, 2 on this line, and we find that point right there. So that's positive 2 and pi over 4. Okay? Now, so these rays sort of project outward from the origin. But let's look at the point negative 2 and 5 pi over 4. So 5 pi over 4 is going in this direction, but if we're going negative 2 from there, we would actually go backwards, which would be away from the origin in the opposite direction. So we go here, and we land in the exact same point. So this is also the point negative 2 and 5 pi over 4. So as you can see, there's more than a single representation for each of these points. If you make the restriction that all your angles are between 0 and 2 pi, and you have positive r values, they're of course unique. But if you take that away, you can have multiple representations of the same point. Here's another example, 2 and negative 7 pi over 4. So negative 7 pi over 4, that's outside of the range of 0 to 360, or 0 to 2 pi, I should say. And so you need to find a coterminal angle in order to plot it. So if we take negative 7 pi over 4 and add 2 pi to that, that should give us something inside the range 0 to 2 pi. That would be the same as doing, 8 pi over 4. So negative 7 plus 8 would give me pi over 4. So this is again the exact same point, 2 pi over 4. So this is another representation of the exact same point. So you lose the concept of uniqueness when you unrestrict those. But there's a lot of advantages that are gained when we do that as well. So we generally allow for these to be these restrictions to be removed. Let's now take a look at converting polar coordinates. So I've got a few points that will go from rectangular coordinates into polar, and then a few more examples going the opposite direction. So we'll see both here. All right, so my first point is rectangular, and it's the point 1, 1. And if it's rectangular, just keep in mind these are x and y coordinates. And what we want to do is convert that into r and theta coordinates. So r, of course, is x squared plus y squared, and then we take the square root of that. And theta is the arctangent of y over x. So that's what we need to apply here. R in this case would be the square root of 1 squared plus 1 squared, which is the square root of 2. Theta would be the arctangent of 1 over 1, which is 1. And the arctangent of 1, if you think about that, it means that sine and cosine would have to be the same value. And that's going to be at pi over 4. And double check your angle measure and make sure it agrees with the quadrant of the original point. Sometimes arctangent will provide you an answer, but it will provide in the wrong quadrant, and you have to adjust for that manually. All right, and it's just a limitation of the function arctangent. So this coordinate pair is just square root of 2 and pi over 4. The next one is 0, 3, and if we apply r equals the square root of 0 squared plus 3 squared, we find that r is just 3, so that doesn't change anything, that's fine. And then theta is going to be the arctangent of 3 divided by 0, which doesn't make any sense because, well, this is division by 0 and it's undefined. But there are certain points where arctangent is undefined, or tangent is undefined. So we can rely on those points, or you can just kind of think of, where is this point really? So 0, 3, 1, 2, 3 would be right here, and that's an angle measure of pi over 2. So there's another way of developing that angle measure. So this would be 3 comma pi over 2. All right, one last example going this direction. I generally start with r because that's usually what I find to be the easiest. It's just a straight calculation. You don't have to worry about any nuances or anything. So let's see here. This would be 25 times 3, so that's 75 plus 25. So the square root of 100, which is 10. All right, so we have the value of r. Now, theta, let's see. It's going to be the arctangent of the y-coordinate over the x-coordinate. 5s will cancel out, and so I'm really looking at the arctangent of -1 over root 3. Okay, and now these might be things that you had worked previously in trigonometry by using a unit circle. You can certainly use a unit circle here, or you can rely on other methods. One thing is I generally only remember the different values of the trig function sine and cosine between 0 and 90 degrees. And the rest of them I just kind of develop based off of quadrantal angles, if they happen to be on the quadrants, or if there's a reference angle that can be used in one of the other quadrants, something of that sort. You can, of course, rely on your calculator, but just the easiest thing to use with your calculator is degree mode. And that's just because it's not quite so easy to tell all the time what type of angle measure you actually have if it's provided in a decimal format. Well, for instance, let me show you. If I take the arctangent and let me put it in radian. -1 divided by the square root of 3. It's not quite as easy to tell what that angle measure is in radians versus degrees. So we do the exact same operation, but now in degrees. Oh, -30 degrees. I know that's the same thing as -pi divided by 6. That's the same answer it was telling us in radian mode, but it's just easier to see it in degrees. And as long as you're quick on converting degrees into radians, you can take advantage of that. So -pi over 6 is the answer that's provided. Here's the thing. 5 root 3 -5, so that's going to be over here in positive on the x, negative in the y. So that is in quadrant 4. But we don't want to answer with -pi over 6. We want to answer some final answer in terms of 0 to 2 pi. So we're going to answer here with radius of 10, and then if we take -pi over 6 plus 2 pi, that will put it in the range that we want. So that would be 12 pi over 6 minus pi over 6, or 11 pi over 6. Sometimes it gets even trickier because you might be in quadrants 2 or 3, and the arctangent will only give you answers in 1 and 4. So you have to always at least check to see if you need an adjustment when using arctangent. Going the other direction, if we're converting polar coordinates into rectangular coordinates, it's generally considered a little easier because you don't have to worry about adjusting the angle measures. So for instance, if you want the x-coordinate of this point, because now this is in r and theta, and we want to convert this into x and y, x is equal to r cosine theta, and y is equal to r sine theta. So in this case, x would be 3 cosine of pi over 3, and y would be 3 sine of pi over 3. Now, you should know your sine and cosine values in the first quadrant. If you don't, it's still forgivable, and you can still use the calculator, but your final answer needs to have exact values. So here's the thing. If you do sine of, let me make sure I'm back in radian mode now, pi over 3, then what you're going to get is something like this. You're not to put that as your final answer, but there's not many values of sine and cosine that you get as a response. It's really either 0, 1, a half, root 2 over 2, or root 3 over 2. So this is either root 3 over 2 or root 2 over 2. Once you figure out which one, now you've got it as an exact answer. It's root 3 over 2. So this would be 3 times root 3 over 2. The other one is a half. So our answer here, our coordinate in rectangular form, would be 3 halves and 3 square root of 3 over 2. The next one, we would get the x-coordinate by doing 2 cosine of 3 pi over 2, and the y-coordinate from 2 sine of 3 pi over 2. Now, if you don't recognize this as a quadrantal angle, you could certainly use the calculator to get the values of sine and cosine here, but 3 pi over 2 is this quadrantal angle right here, and on the unit circle would be a point which is at 0, negative 1. So this would be 2 times cosine of that is 0, and then 2 times sine of that angle is negative 1. So 0, negative 1, 0, negative 2, sorry about that, would be our coordinate. Lastly, we would get the x value of this coordinate by doing 6 cosine of negative 5 pi over 6. Or, of course, you could transform that into an equivalent value within the range of 0 to 2 pi, and it might make it easier. So negative 5 pi over 6, if I do that value plus 2 pi, so that would 2 pi would be 12 pi over 6. So this is really 7 pi over 6. I'm not really sure that that's a whole lot easier to work with there. Regardless, you can, of course, use your calculator here. And just make sure you give exact answers in the end. So I would really recommend just getting the angle measure or the sine and cosine of the given angle measure, and don't multiply it by 6 just to kind of help you figure out what the exact value is. So like for instance, if I do cosine, and you know what, I'll go back to the negative 5 pi over 6, just because if I made a mistake finding that, then that's going to throw my answer here. Why do I keep typing the wrong value? There we go. So that's negative root 3 over 2. So 6 times negative root 3 over 2. And the other one should be a half. So sine negative 5 pi over 6, negative 1 half. So 6 times negative 1 half. So that means I have the coordinate 2 goes into 6 3 times, so negative 3 square root of 3 and negative 3.